All right, so today's set of lectures will be a little shorter than usual. But before we wrap up, I want to say one more thing about coin change. And this has actually some kind of interesting broader ramifications for algorithms and optimization in general. So occasionally when I teach this class, a student comes to me and they say, hey, look, this DP algorithm for making change is inefficient. And it seems like we ought to be able to do something smarter. And they propose something that sounds like this. So here's something that I call the pseudo-greedy algorithm for making change. So, I'm not going to give you this algorithm formally, but the idea is something like this. It feels like if I've got a big amount that I'm trying to make change for, what I should be able to do is use a lot of my big denomination, get myself as close as possible to this final amount, and then once I'm close, by some standard, then I switch to the DP algorithm and use the DP algorithm to fill in the last gap. So the idea here is, all my examples, I'm making change for like 6 and 10, but what if I'm making change for 1,000? Then wouldn't it make sense to just throw in a ton of 4s? And then once I've thrown in a ton of 4s, once I'm within 8 or something like that, I'll use the DP algorithm to fill in the gap. So idea is use many of best coin. Now I'm not going to call it the best coin. Use many of the biggest coin to get close. And you can get creative about what close means. Does close mean within like 2 of your biggest coin, or maybe within like the sum of all your denominations, or maybe close means halfway there or something like that, right? Use many of your biggest coin to get close, and then fill in the rest with DP algorithm. Right, we've seen already that a pure greedy algorithm doesn't work. Right, a pure greedy algorithm where I just use as many of my biggest coin as possible is not guaranteed to give me the best change, because what it might do is it might kind of use up extra space. It would be more efficient to have used some smaller coins. And so this pseudo-greedy algorithm feels totally right. Like it feels like this should totally work. Unfortunately, it does not. Right? This is not a correct algorithm for choosing optimal change. Like it's a fast algorithm. It's one that will, you can throw a whole bunch of coins down quickly and get close. But it's not an algorithm that is guaranteed to get you the optimal change. And so here's my favorite example for this. So here's my counterexample to the idea that this algorithm gives us optimal change. So suppose D, my denomination set, is 1, 10, and 11. And, isn't it interesting that every time I talk about coins, I use a 1 and then some number and the next number, right? So 10 and 11 are really close together. Maybe there's something interesting about that makes this a challenging, denomination set. Okay, so what is optimal change for 110? Here's my question. Optimal change for 110. All right, so let's let n equal 110, and let's think about what optimal change is. So if I run the DP algorithm, okay, and so let's run DP algorithm. And what'll this do? Well, it'll take about 330 steps. I've got 3 denominations. I'm making optimal change for 110, so I multiply m by n, and that's about the number of steps. So that's about 330 steps. All right, so it's not fast. It's not like the slowest thing you've ever heard of, but it's not really fast. And it gives me the answer. Now, what's the optimal answer? I hope it's pretty obvious that the optimal thing to do here is to put down 10 11-cent coins. right? What is my optimal? 10 times 11. So let's write it like this: 10 11-cent coins. Okay, and so what we see is, we have this large N, and this feels like it confirms our intuition that the pseudo-greedy is a good idea, because what we could have done is just said, oh, N is large, now let's put down a bunch of 11s, and the first 9 or so 11s, 8 or 9 11s, would have been really fast, and then we could have used the DP algorithm to find optimal change and sort of verify optimal change for the last 20 cents or something like that. In this case, it'd be the last 22 cents. And so it feels like that tells us that, okay, this is looking pretty good. So now let's ask another question. Let's ask the question, what if we're asking for optimal change for 91? All right, and now let's use the intuition that we got from 110. And let me leave my denominations on the screen. And try to design a pseudo-greedy algorithm that does this. And so what our pseudo-greedy algorithm will do is it will get within 22. Okay, that's 2 of the biggest denomination. It'll throw down 11s just one by one until it's within 22 of 91, and then it will stop and fill in the rest optimally. Okay, so what do we have? Well, if I put down 7 11s, so 7 times 11, whoops, that puts me to 77. Now that's within 22 of 91, right? So that's close. It's not like within an 11-cent piece, but it's close. And so now I've got 7 11s. What's remaining? Well, the change remaining to make, so remaining change is 91 minus 77. What is that? Well, that's 14. Right? So how do I make change for 14? Well, that's an 11. 1 times 11. And 3 ones. Okay. So 4 more coins. So 7 plus 4 is, in total, that's 11 coins. Okay. So 7. So in the end, I've got 8 11s. So my final change is 8 11s and 3 ones, okay? Or 11 coins altogether. 11 total coins. Okay, is this optimal? Okay, I hope that it's clear that it's not. Okay, it might not actually be obvious what is optimal, but 11 is not. And why is that? Well, because I could have just used 9 10s to get me to 90 and a 1, right? So this is not optimal. And the way I can tell that it's not optimal is I can show you that there is something better, right? What I'm showing you is actually not optimal, but it is better. Okay, so what is better? Well, better is 9 10s plus 1 1. And so that's 10 total coins. And what's interesting is that I can actually outperform this pseudo-greedy algorithm using 0 11s. Okay, so we have this intuition somehow that if I have a large change amount, I'm going to use mostly my biggest coin, right? And that only makes sense, right? That my biggest coin would show up a lot if I'm trying to make a lot of change. And it's this greedy intuition that says, let's try to get as close to our final solution as possible. Let's try to get as close to the optimal solution as we can. The way we do that is we use large coins, right? It seems to make sense. It turns out it's completely misleading. And in this case, we can actually do better than the pseudo-greedy, right? Better than something that uses that intuition without using any 11s at all. Okay, so here we can improve without 11-cent coins. So it turns out this isn't optimal. The optimal uses 8 10s and 1 11, right, for a total of 9 coins. But that's neither here nor there. So the optimal ends up being neither of the things that we initially landed on. But what this does is this betrays a very dangerous intuition. So our very dangerous intuition is very subtle, but it can lead us down the wrong path if we're in the wrong context. So the very dangerous intuition is essentially this greedy intuition, and I think that the simplest way to express it is it's this greedy intuition, and I think there's more complicated ways to express it that I'll try to express in a minute here. But the dangerous intuition is that the way to do best is to get as close to your destination as possible. And that just need not be the case in optimization. So the intuition is to do best, move as quickly to your destination as possible. I'll say as quickly towards destination as possible. Okay, and that just need not be the case. So a more subtle, I think, thing that sometimes can lead us into this trap is assuming that the math of continuous numbers can kind of be dragged and dropped directly onto the math of discrete numbers. So it turns out that if you could split coins in half or into arbitrary fractions, then the greedy algorithm would actually be optimal for the coin change problem. And many of you got stuck in this rabbit trail on one of the homeworks thinking about the greedy algorithms for the knapsack problem, because there is also a greedy algorithm for a knapsack problem where you can cut items into pieces that is optimal for that problem. Okay, and so we have a feeling that greedy algorithms ought to be optimal. I think sometimes that feeling might come from having correct intuitions about how continuous math works, but then you just can't take intuitions about continuous math and put them directly into facts about discrete math. Right now that we're working in algorithms, we're largely working in the world of discrete math, and in discrete math, the greedy intuition is wrong, and intuitions that we bring with us from continuous math are wrong. So let me just wrap up by writing a quick note that our pseudo-greedy intuition, or maybe I could say our greedy intuition is often correct in continuous math. So math where we're dealing with real numbers and arbitrary fractions, and instead of having like discrete objects that we're trying to manipulate. Continuous math. Okay, but just because it's true in one branch of math does not make it true in our current branch of math.